Hi everyone, we continue with Chapter 4, Exponential and Logarithmic Functions, specifically Section 4.3, Logarithmic Functions. So say we have that we know from powers that 8 is equal to 2 to the power of 3. So this is the exponential form of this expression. Now logarithms are simply the inverse of the exponential form. And to write this in logarithmic form, we would say log base 2 of 8 is equal to 3. You can see that here. Notice that it says x equals b to the power of y. So y is the exponent and b is the base. In logarithmic form, we would say y, which is the exponent, is equal to log base b of x. Then you can see here on figure 4.5 that y equals log b of x is the reflection of y equals b to the x across the line y equals x. So this here is the exponential function, y equals b to the x, and this is the logarithmic form of the function, y equals log base b of x. So now let's take a look at example 4.8, and it says find the value of each logarithm without using a calculator. So for letter A, we have log base 7 of 49. So what does this equal? It equals 2. Why? Because we know that 7 squared is equal to 49. For B, they want us to find log base 5 of 1/5. This will equal -1. Why? Because 5 to the power of -1 is equal to 1/5. For C, we have log base 6 of the square root of 6. So we know that this is 1/2 because 6 to the power of 1/2 is the same as saying square root of 6. For D, we have log base 4 of 64. And this equals 3 because 4 to the power of 3 is 64. Finally, letter E, log base 10 of 0.001. So the answer to this is -3 because we know that 10 to the minus 3 is equal to 1 over 1,000, which is the same as 0.001. So let's continue with example 4.9. And it says, find the domain of the function f of x equals log base 2 of 4 minus x squared. Now before we do this, let's go back to figure 4.3 and let's recall that the logarithmic function is the inverse of the exponential function. So remember that for exponential functions, we had that the range is y greater than 0. So the range is always positive. Now, because this is the inverse, so the logarithmic function is the inverse of the exponential function, we know that the domain is x greater than 0. So that means that this expression here, 4 minus x squared, has to be greater than 0. So we have to find the values of x that make this expression greater than 0. So we can find that out by finding the critical points. We can do that by factoring first of all. So notice that this expression is a difference of squares. So it can be rewritten as 2 minus x times 2 plus x. So that means that the critical numbers are going to be x equals 2 and x equals -2. So we can build a little table where we have -2 and 2 and test values before negative 2, after negative 2, but lower than 2, and then values that are greater than 2. So something that is less than negative 2 would be negative 3. So notice that if we plug in negative 3 into this expression here, we're going to get positive. It would be positive 1. And then here we would get negative. So that means that before negative 2, any value we plug in is going to be negative. Therefore, no solution for the logarithm. Then we can plug in a value between negative 2 and 2, say 0. So notice that if I plug in 0, I'm going to get 2 for this expression and 2 for this one as well. And 2 times 2 is 4, which is positive. So anything between negative 2 and 2 will be positive. And then something higher than 2, like 3, is going to give us a negative. That means that the allowed domain is going to be values of x that are between negative 2 and 2. So on the next slide, you're going to find some of the basic properties of logarithms. So for b greater than 0 and b not equal to 1, that's the base, the following statements are true. Log base b of 1 is equal to 0, because any base b to the power of 0 is equal to 1. Log base b of b is equal to 1, because any base b to the power of 1 is equal to b. For number 3, we have that log base b of b to the power of x is equal to x. Why? Well, because b to the x equals b to the x. For property number 4, we have that b to the power of log base b of x is equal to x, because log base b of x is the power to which b must be raised to get to x. On the other hand, we have a couple of interesting definitions here. First of all, we have the common logarithm, and that has to do with log base 10. Now, log base 10 is used so frequently that we normally don't write the base. So log base 10 of x is written as log of x. So the logarithmic function with base 10 is called the common logarithmic function, and you will find it on your calculator denoted by log. The value of the expression log base 10 of 1,000 is 3, because 10 to the power of 3 is 1,000. Generally, for common logarithms, we omit writing the base of 10. Hence, log is written with no base indicated. It is assumed to have a base of 10. For example, log 0.01 is negative 2, because 10 to the power of negative 2 is 0.01. So the other logarithmic function supplied on calculators is the logarithmic function with the base of Euler's number. So log base e of x. Now, this function is known as the natural logarithmic function, and it is the inverse of the natural exponential function y equals e to the power of x. So it's known as the natural logarithmic function, and it is denoted by the symbol ln, logarithmus naturalis. So that's why we have ln x is the equivalent of log base e of x, natural logarithm of x. So next we have example 4.10, and it says evaluate each expression. Find an exact value without using a GDC if possible. Otherwise, use your GDC to approximate the value to 4 significant figures. So letter A, log of 1/10. So notice that this is the same as saying log of 10 to the minus 1. Therefore, the answer here is minus 1. Log of the square root of 10. Well, this is going to be 1/2. Log of 1. This is going to be 0, because 10 to the 0 is 1. And then here, for D, we just apply property 4, and we know that this equals 47. So 10 to the power of log of 47 is 47. And then for letter E, we have log of 50. Now this we cannot do manually. We will need the GDC. So if you plug in log 50 in the GDC, you're going to get approximately 1.699. That's rounded to 4 significant figures. For f, we have natural logarithm of e, that's just going to be 1. For g, we have the natural logarithm of 1 over e to the 3. So this is going to be negative 3. We have the natural logarithm of 1, which is 0. We have e to the power of the natural logarithm of 5 from property 4. We know that this is going to be 5. And then finally, we have letter j, which we cannot do manually. So we plug natural logarithm of 50 into the calculator and we round it to 4 significant figures. So this is approximately 3.912. So next, let's take a look at example 4.11. And it says, the diagram shows the graph of the line y equals x. So this is the line y equals x, the dotted line. Curve A is the graph of the equation y equals log x. So this is here, y equals log x. Curve B is the reflection of curve A in the line y equals x. Part A, write the equation for curve B. So that's pretty simple, right? Because it's the inverse of y equals log x. Then we know that the blue line must necessarily be y equals 10 to the x. For B, it says write the coordinates of the y-intercept of curve B. So we know that curve B is y equals 10 to the power of x. So that means that we can find the y-intercept by plugging in 0. And we know that 10 to the 0 is equal to 1. Therefore, the y-intercept of curve B is going to be 0, 1. On the next slide, you're going to find some properties of logarithms. But before we take a look at the properties themselves, let's recall some properties of exponents. So remember that if we have b to the m times b to the n, that equals b to the power of m plus n. If you have b to the m over b to the n, that equals b to the power of m minus n. And finally, if you have b to the power of m and that to the power of n, that equals b to the power of m times n. So, given m greater than 0, n greater than 0, and any real number k, the following properties are true for logarithms with b, base b, greater than 0 and not equal to 1. So property number 1, log base b of m times n is equal to log base b of m plus log base b of n. So that means that the log of a product is the sum of the logs of its factors. Property number 2, log base b of m divided by n, this one here, is equal to log base b of m minus log base b of n. In other words, the log of a quotient is the log of the numerator minus the log of the denominator. And then property number 3, log base b of m to the power of k is equal to k times log base b of m, meaning that the log of a number raised to a power is equal to the power times the log of the number. So any of these properties, this is important, any of these properties can be applied in either direction. So let's continue with example 4.12, and it says use the properties of logarithms to write each logarithmic expression as a sum, difference, and or constant multiple of simple logarithms. Okay, so let's take a look at letter A, and it says log base 2 of 8x. So according to the properties of logarithms, when you have a multiplication, such as this one, 8 times x, you can separate it into a sum. So you can rewrite this as log base 2 of 8 plus log base 2 of x. But log base 2 of 8 is 3, because 2 to the power 3 is 8. So we can write it as 3 plus log base 2 of x. For b, we have natural logarithm of 3 over y. And from the second property, we know that this is natural logarithm of 3 minus natural logarithm of y. For c, we have log square root of 7. This is the same as log of 7 to the power of 1/2, which we can write as 1/2 log 7. For D, we have log base B of x cubed over y squared. So we can write this as log base B of x squared minus log base B. Let's x squared or x cubed? Oh, sorry, it's x cubed. X cubed, so this is x cubed. Log base B of y squared. And then this would be equal to 3 times log base B of x minus 2 log base B of y. Then we have E, letter E, where we have natural logarithm of 5e squared. So we can separate into sums. Natural logarithm of 5 plus natural logarithm of e squared. And this is the same as natural logarithm of 5 plus 2. And then finally, we have f log of m plus n over n. And this is simply going to be log of m plus n minus log of n. Now be careful, because recall that log of m plus n is not equal to log of m plus log of n. This only applies to log of m times n. Okay, so now let's take a look at example 4.13. And it says, write each expression as a logarithm of a single quantity. So this means the opposite process that we did in the previous example. So notice that for A, if we have log 6 plus log x, we can express it as the logarithm of a single quantity as log of 6x. For B, we have log base 2 of 5 plus 2 log base 2 of 3. We can have this as log base 2 of 5 times 3 squared. Where do I get the 3 squared from? Remember that we can send this here as an exponent. So then this will give us log base 2 of 45. For letter C, we have log, or natural logarithm, I should say, natural logarithm of y minus natural logarithm of 4. And then this is going to be natural logarithm of y over 4. For D, we have log base B of 12 minus 1/2 log base B of 9. And we can rewrite this as log base B of 12 minus log base B of 3. We can send the 1/2 as an exponent of 9, and 9 to the 1/2 is the same as the square root of 9. And then finally, this would be log base B of 12 over 3, which is log base B of 4. Then for E, we have log base 3 of m plus log base 3 of n minus 2 log base 3 of p. So notice that this is going to equal log base 3 of m times n over p squared. And then finally we have f, which is log base 2 of 80 minus log base 2 of 5. And this is going to equal log base 2 of 80 over 5, which is equal to log base 2 of 16. And this is going to equal 4, because 2 to the power of 4 is equal to 16. So now we have example 4.14, which will be the last one on this video. But before we do it, we need to learn a formula regarding the change of base. So it says, let a, b, and x be positive real numbers such that a does not equal 1 and b does not equal 1. Then log base b of x can be expressed in terms of logarithms to any other base a, as log base b of x is equal to log base a of x over log base a of b. So you might be wondering, why is this so? Well, let's say that log base b of x is equal to some y. This implies that b to the power of y is equal to x. And then if we apply any logarithm of any base, let's say log base a to b to the power of y is equal to log base a of x. We're just applying a logarithm to both sides of the equation. And then from the properties of logarithms, we know that we can rewrite this as y times log base a of b is equal to log base a of x. Therefore, y is equal to log base a of x over log base a of b, as we stated over here. Okay, so now let's focus on the example 4.14. And it says, use the change of base formula and common or natural logarithms to evaluate each logarithmic expression. Start by making a rough mental estimate. Write your answer to 4 significant figures. So for letter A, we have log base 3 of 30. So an estimate, a guesstimate of this would be 3 to the power of what equals 30. So we know that 3 to the power of 3 is 27, and we know that 3 to the power of 4 is 81. So it has to be a little bit over 3. So let's do the change of base. We could use either one. We could use natural logarithm or the common logarithm. So let's use the common one. Log of 30 divided by log of 3. Now you could have also done it with natural logarithm. Natural logarithm of 30 divided by natural logarithm of 3. And both would give you approximately 3.096 to 4 significant figures. For letter B, we have log base 9 of 6, which we can rewrite as natural logarithm of 6 divided by natural logarithm of 9, or if you prefer, log of 6 divided by log of 9. And they both should give you approximately, well, we didn't do the guesstimate. So what would be the guesstimate? 9 to the power of what is 6? Well, it can't be 9 to the power of 1, because that would be 9, which is larger than 6. And it can't be 9 to the power of 1/2, because that's 3, which is way below 6. So it has to be almost 1. If you plug that into the calculator, you're going to see that it's actually 0.8155 to 4 significant figures.